Example 2. A study was planned to examine the length of a certain species of fish on Gull Lake. The initial plan was to take a random sample of 100 fish from this lake using a special net, examine our results. Numerical summaries on lengths of the fish measured in this study are given. Use them to answer the questions. Part A. Create a 95% confidence interval to estimate the average fish length for the entire lake. Part B. We want to be more accurate about our estimate of the average fish length in Gull Lake. We want to be within 0.25 inches, in fact. How many fish need to be sampled in order for this to happen? Let's look at Part A. We'll first go through our conditions. We're assuming independence, simple random sample. Certainly 78 fish is less than 10% of all the fish in the lake. And since our sample size is bigger than 30, we don't really have to worry about the nearly normal condition. So let's look up our t-statistic in the table. Again, we're doing a 95% confidence interval. So our t-statistic would be, we look at degrees of freedom. 80 is as close as we can get. Degrees of freedom will be 77, right? N minus 1. 78 minus 1 is 77. But 80 is as close as we can get on our table. Looking over at the 0.025 or 95% of the column, we get 1.990. On the calculator, we can just put 0.025 for the area. DF at 77. We get 1.9125. So if we use this value and plug everything in, we have 25.018 plus or minus 1.99125 times 4.1831 over root 78. So our error term is 0.9431. We add plus or minus to 25.018. We are 95% confident that the true mean fish length for this lake is between 24.075 and 25.961. So using technology, we're going to press Stat, scroll to Tests, select T-interval. We're going to choose Stats rather than Data. Again, Data, we'll do one of these here in a minute. We'll use Data if we have the raw data. We don't have the raw data. We're given summary statistics, so choose Stats. And we input in our X-bar at 25.018. Our SX sample standard deviation is 4.1831. Our N is 78. Confidence level 95, and press Calculate. We get exactly the same interval we did when we got by hand. Occasionally, again, you'll be off in the rounding, particularly if you use the table. Similar with StatCrunch, similar as we did last time. Going to go to Stats, T-Stats, one sample with summary. Going to put in our summary statistics, choose 95% confidence level, and press Compute. Again, we get the same thing we obtained by hand and with the calculator. Lower limit 24.07, upper limit 25.96. Now let's look at the B part. Let's think about how we can estimate the sample size to get within a certain margin of error. So again, our margin of error term is this plus or minus t star times the sample standard deviation over the square root of n. So let's bring that out. That's our ME. We did a similar development with proportions. Could be tempting to use this formula for constructing a confidence interval, break it out, the margin of error, solve for n, and then set this term less than or equal to a particular margin of error. So again, there are a couple problems with this. We don't know S. I mean, how can we know the sample standard deviation before taking our sample? We have a similar problem with proportions. Recall that our critical value t sort of depends on our sample size, which is what we're trying to find. So one method that's used is to estimate the population standard deviation sigma based on prior studies and use the one sample z interval. I said we don't for constructing intervals, but we can use a form of it to estimate the value of n needed for a particular margin of error. We can solve for n to get n is greater than or equal to z star times sigma over the margin of error, all that squared. However, similar to proportions, I prefer this first form. I already know the margin of error term is, and I don't really want to have to remember another formula. So let's see how we can use this formula in our problem. So again, we want to estimate within 0.25 inches how many fish need to be sampled. So our ME is 0.25. Z star, we're going to stick with the 95% confidence. Our sigma that we had from that previous study we're going to use is 4.1831. So margin of error, it's got to be greater than or equal to Z star sigma over root n. We plug all this in. solve for n, multiplying both sides by root n, dividing by 0.25, we get, and we simplify the right side, we're going to get root n is greater than or equal to 32.7955. Squaring both sides, we get n has to be greater than or equal to 1075.5. So we'll round that up to 1076 would need to be our sample size to get within 0.25 inches for a margin of error. So if we use the formula that's already solved for n, it does computationally come out a little better, but again, we got to remember the formula. So let me show you this development real quick. So n greater than or equal to z star sigma over me, all that squared. We plug everything in, we square it out, we get exactly the same number,